Okay, so I'll
Wrong
just
component.
I'll
Yeah.
introduce. Okay, so hi everyone. This is our first recording for the Wolfram language track, and today with me is going to be Anthony and Mihir. So before we talk a little bit more about Wolfram language, I'm going to let them introduce themselves.
Yeah. Hey guys, I'm Anthony. I'm a rising junior, based in Massachusetts, and I'm excited to work with you guys.
Hi, my name is Mahi. I am from Dhaka, Bangladesh, and I'm a high school student.
Yeah, so today we're going to go over the first few chapters of the textbook, The Elementary Introduction to the Wolfram Language, which is going to be our main resource for the Wolfram language track. And we're just going to go over the basics of the Wolfram language so you have a pretty good foundation and a few practice problems. And so a link to the textbook and a cloud notebook with all our work is going to be put in the video description after this. So you can check that in more detail. But without further ado, I'll let Anthony take it away with the first two chapters.
Yeah, so the first two chapters are the most basic ones in the book. In the first chapter, we'll be going over some basic arithmetic, such as addition, subtraction, multiplication, division. And then in chapter 2, we'll learn some commands that does some calculations for us. So the first thing that we have to know is when you do 1 plus 1, in order to run this line, we have to press Shift Enter. So that gives us 2. So basically, addition, as you all know, is like, I'll just give one more example of this. That gives us 110. And subtraction works the same way. 100 minus 10 is equal to 90. And I'm always pressing Shift Enter in order to run that command. So it should be really straightforward. Then multiplication, say we're doing like 8 times 9, shift and then 8, the star sign is multiplication. And if you just do 8 and then just this space and then click 9, it's also basically multiplication too. So there's two options to write, to do multiplication in Mathematica, and then division, slash sign, it gives us division. So these are all of the basic addition, subtraction, multiplication, and division. And that is basically all of chapter 1. So just a few, I guess, practice problems that that you guys could try out is, let's say, well, since for like really simple ones, like that could be number 1. Then for number 2, these are really simple, and then the third one could be write 3, just write like 3 different multiplication that gives 100 as the answer. So I guess that's another good one. And then just copy and paste that. Write 3 different division that gives 4 as the answer. Yeah, so those are just practice exercises to try out. It should be really straightforward. And that is it for chapter 1. So chapter 2 is called Introducing Functions, and it's also very similar, but the different thing from chapter 1 is that in chapter 1 we actually coded 1 plus 1, but there's commands that do that. So the plus command is the command for that. Sum is, I guess it's not, but plus gives 1 plus 1. So, and then times is the multiplication one, and subtract should work. Yeah. And then the 5, 6, 2. This also works too. So these are the 4 commands of addition, subtraction, multiplication, and division in Mathematica. And just for reference, if there's any command that is confusing, just press question mark and then subtract, and then shift enter, and that gives us how to run the command. So this is a more detailed explanations and examples that Wolfram provides. So that's just a good resource to have it too. And yeah, so chapter 1 and 2, very basic information, some practice problems.
Anthony, two other functions you might want to quickly go over are also like the max function and random integer function.
Okay.
Also two things.
So the max gives us, so if we type in like 1, 2, 3, 4, 5, this is just a really basic example. Just it gives us the largest value out of it. And then for the min, same thing. Also gives us the smallest value for the min. So yeah, so these are max and min are two more functions. And wait, Rohan, what was the last one?
Also with the random integer function. Yeah.
Yeah, so random integer. Random integer.
Yeah, and then we just call the number we want between 0 and whatever number, and it will generate. So like if you put in, or if you just put in 100 for a random integer, that will give us a random integer between. It just takes in the highest number though.
Let's figure this out. So in the range, yeah. So formatting was a little confusing there. So if we put in 1 to 100, that's the range, and 77 just gives us a random integer.
Or you could also just put in 100 too, I think. And it will assume, if you put in 100, it will assume it's like 0 to 100. Yeah, so that also works.
And just one thing, there's also something called seed random, which we do. So say like 100. And the good thing about seed random is that this basically, if we run the same code over again, okay, so if we run the same command twice, we'll get different values here. But if we put in seed random, even if we run the same command, okay.
I think maybe because you called it 2 times, right? Or
yep, probably.
So yeah, you just got
Okay,
1 to both times.
Cover that next time. But anyway,
But
random integer works
yeah.
this way. And then some practice problems. Number 1 could be just, I guess we don't have to go over the addition multiplication.
Yeah, there are also some practice problems in the textbook. But for this stuff, it's pretty basic. So yeah, these are the first 2 chapters. Like Anthony showed us, you call these basic operations using like symbols, but there's also underlying functions which we can call them into, and that's a hallmark of the fact that the Wolfram language is a functional language, so we can represent everything through functions and function application, and we'll start to see a little more of that as we get deeper into these chapters. So Mihir, do you want to start chapters 3 and 4? And for these,
I'll just have one more thing.
Okay. Yeah.
I'm just writing one practice problem. So after generating 3 random variables using random integer from 1 to 1,000, find the average by using addition and division. So solving this problem you'll be able to use random integer and then addition and division. So I think it's a good problem to practice. And yeah, that's it for chapter 1. So I'll hand it over to Mahir for chapter 3 and 4.
Mm-hmm. So Mahir,
Hi, my name is Mahir, and I'll be sharing chapter 3 and 4 with you. So I'm starting my screen share. Just give me 1 second. So I'm going to through the basics of the chapter 3 and 4 now. One minute.
Yeah, so in the meantime, I can give a quick overview of what chapter 3 and 4 are going to be about. So we looked at the idea of functions in these first few chapters. Chapter 3 and 4 talk a little bit more about specific functions and lists or arrays in the Wolfram language. And so the general theme as we move through this book is really just going to be learning more functions and how to use more functions, because the Wolfram language is sort of a functional programming language taken to the extreme in the fact that we have functions to do so many different things. And I think we mentioned this on the competition website as well. So Mihir, are you okay? Yeah.
Can you see the right screen, Rohan, please? Can you?
Yeah, I can see your screen.
So the chapter 3 starts from here. So it's chapter 3 is mainly about
Lists.
1 minute. Chapter 3 is mainly about list. So we create list. Lists are basically the arrays of any programming language, but in Wolfram language, list can contain graphics and like numbers, strings, etc., etc. Like almost anything that you can put on. So okay, so let me go through this. Okay, so here is a basic list. Okay, so I put an integers and some alphabets here, and Wolfram manages to handle all of them. And
So
I
wait,
can also,
before we go over that, we should acknowledge the fact, first of all, that A and B here have been defined to variables beforehand. So that's why they're evaluating to 40 and 60. And then also, you might notice that we just typed in a C and it returns a C in the Wolfram language. Usually in many programming languages, you can't just type in a character. We'd have to make it a string or something like that. In addition to being a functional language, the Wolfram language is also a symbolic language, which means that we can type in any sequence of symbols from our computer that aren't a string. They just represent a symbol, and they're still a valid expression in the Wolfram language. They are just not bound to any value yet, but we can do arithmetic with them. So for example, here, if you want to just type in x plus y, so we can see what that does. In a normal programming language where we haven't defined x and y yet, and then run that with shift enter. So here it just returns x plus y as a valid expression. In a normal programming language, if we didn't define x and y yet, the computer would sort of give an error. But because the Wolfram language is symbolic, it realizes that it doesn't matter what the values of x and y are right now. It's just some operation applied to these two symbols. And then maybe later down the road, we want to put in a value for those symbols. So that's why we can just put in a C and it evaluates back to a C. But yeah, you can take back over.
Okay, so in here, so just to make one thing clear about what Rohan said, so I'm just going to try to change the values of B and C, so it's clear to everybody. So if I type A is equal to 17 and then B is equal to 19, then I can run it again. Yeah, here. So A is equal to 17 and B is equal to 19. So in the new list, like it's the last two elements are 19 and 17, where the B and C stays. And if I just like and the C stays C because it's not defined yet, it's just alphabet. With list, we can plot the list with a function called list plot. So I have taken an array and like I have listed them on a graph with this function, and we can also like list some things from range 1 to 0. So this range here just basically says that list the numbers from 1 to 10.
Right.
In Wolfram language, we don't need to define from where I is starting. Like if we define a for loop in other languages, we need to define from where it starts. But in Wolfram language, it starts from 1 by default.
Right. Yeah, that's an important point. We do 1 indexing. So a lot of programming languages start with 0 as the first element. In Wolfram language, this is a little bit beyond where we are right now, but if you actually try to look at the 0th part of a given expression, it will tell you the type of that expression rather than the element that is the first element. So we always start with one indexing.
And here we can also put the list in a variable. So I have just put it in, and if I just type to, it's going to print out the same variable here. So I don't need to write the range 10 again and again. I can just use it. Like writing is more easier than range 10.
Well, actually, yeah, you have to execute that line though. Go back up. You have to run that line. You haven't run a equals range 10 yet.
Oh, yeah.
Because that's why it's still printing out 17 there. So if we run that line and then we run the expression beneath it again, then that will print out the list. Yeah. So that's an important thing to keep track of. Since this is like a REPL environment, the variables we defined earlier will still be defined down below. So just be careful of the fact that like you might be getting weird errors because your variables are set to other values and that you wouldn't expect if you reuse a bunch of the same similar symbols like X, Y, A, B, stuff like that.
And yes, in the bottom here, I have just list plotted the values of X. So if I execute that, it's just going to plot the values of A, and it's just simple as that. So now I use two functions here. So I have first is list plot function to list them into graph, and then I have used range function in the list plot function. So it's basically what does it plots numbers from 1 to 20 in the graph. And now we have the reverse function, which actually reverse the range, reverse the list from downside to upside. Like 4 was the last element, and now 4 is the first element, and 1 was the first element, and now 1 is the last element. That's basically what reverse does. And in this example, I have put range 10 directly in reverse, so it just prints from 9 to 10, decreasing 1 at a time. And now we have list plot. So now I have list plotted the reverse range 10. So I have used 3 functions at the same time to plot from 10 to 1 in a graph. Now it's time for the join. So what join function does is basically add the list. It's very simple, like add the list and like remove the brackets, and it will be whatever, it will be a single list.
Yeah, so it just takes a bunch of smaller lists and it puts them into a bigger list and it joins them together in the order we put them. So for example, if we had put the sublist 4, 5 as the first parameter and the sublist 1, 2, 3 as the second, then it would read 4, 5, 1, 2, 3, 6, 7. So it just joins them in the order we give them here.
Yeah. So and this also does the same actually. And in the join, so I have and in the join I have joined range 1 to 3 from 1 at a time, and then range 1 to 5. So it just prints 1 to 3 and this 1 to 3 for 5. And now I have list plot. So what it does is list the one minute. Why it does.
Right. So what this list is doing is it's going from 1 to 20 with range 20. Then we have this discontinuous jump back to 1 because range starts at 1 again. So it goes 1 to 20. Then we jump back to 1, and this time we go 1 to 30. So that's why it's producing this weird output, because the lists are discontinuous. But this is just another way of showing that we can apply the same sort of functions to any sort of list. So even lists that don't really have a smooth, not a smooth, but like a continuous sort of plot.
Okay, so thank you, Rohan. And this list function here done from 1 to 20 here, and then it goes down from 20 to 1, and then it again goes up from 1 to 30 because I have the reverse function in the middle, so it just goes down in the middle of the road. And I think I am done with the
Yeah, for chapter 3, why don't we try one of one of the practice problems from the textbook? So one of those problems is use range, reverse, and join to create the list 3, 2, 1, 4, 3, 2, 1, 5, 4, 3, 2, 1. So you might want to just type that out somewhere below. So okay, the elements of the list are 3, 2, 1, 4.
Can you please put the problem in the chat, Rohan?
Sure.
That would be nice. Thank you.
Basically, it's just making sure that we know how to use the functions you just went over. So you could just paste that into the notebook if that makes things easier.
So here is the problem.
Right.
So I need to create this this 3 2 1 4 3 2 1 and then 5 4 3 2 1.
Right.
So now I'm going to try this problem. So
yeah, and the important thing to do with this problem in particular is right now we know how to generate consecutive lists of consecutively increasing or decreasing numbers. So we need to split this up into the consecutive decreases and increases and then just join them together, which is what Mihir is doing. So we see that 3 2 1 is a consecutive decrease, 4 3 2 1 is another consecutive decrease, and then 5 4 3 2 1 is a final consecutive decrease. So we can create these consecutive decreasing lists and join them together. So Mihir will show you how to do that.
So first I'm using the join function because I have to join them together. And then I'm going to use reverse and then range. And first we have a range of 3 and then we have a 1, 2, 3. We have a reverse of 4.
Range of 4.
Oh yeah.
Yeah, no, it's okay. That, and you guys have probably noticed this by now, but all the sort of inbuilt functions in the Wolfram language are capitalized. So it's generally good practice to start functions with a lowercase that you're going to define yourself, which we'll go over a little bit later. But that's how you sort of distinguish between those which are defined by the language and those which are not.
Yeah.
And so the last one should be reverse range 5 because we start from 5 and go down to 1. So the last, yeah. But then otherwise that should produce, yeah, that produces exactly what we see there. So there are a bunch of other practice problems like this you can look at, but it's all just this idea of combining these 3 functions to create different lists. And so, yeah, these functions are pretty useful, actually, maybe more than you'd expect at first, because so much of what we do in the Wolfram language is just like mapping operations over lists. But with that said, we can try and go on to problem 4, which shows us how we can make other visualizations of lists. Like we've seen the list line plot so far, but there are other sorts of visualizations we can make. So Mihir, do you want to start on that?
Can you please place the problem?
Oh no, we're just moving on to chapter 4, not a specific problem, but
I had the wrong.
Yeah. So I think
1 minute, just 1 minute.
Sure. So I think we should also probably go over the fact that like, where are these visualizations coming from? I mentioned that everything in the Wolfram language is symbolic. So these visuals are also represented as symbols. And so maybe we'll do this another time, but you can take a visual, copy and paste it, and then plug it into another operation. It's not just a picture. It actually has a meaning within our Wolfram notebook because it's a symbol with a meaning. So
it's actually copyable.
Yeah, so you can click it, copy it, and then put it in another operation. And if that operation makes sense on a plot, then it will actually produce an output, which is pretty cool because that doesn't really exist in any other sort of programming environment.
I got it from the earlier and just pasted it like a character.
Right. And the important thing about that is it's actually not just an image, but it's a symbol with meaning in our notebook that we can use in other code, which sort of extends to some of the similarities between the Wolfram language and Clojure because they both have roots to Lisp, although Clojures are a bit more apparent. And maybe that's something we can talk about in a future video as well. But otherwise, we can start with chapter 4.
Okay, so chapter 4 is displaying list. So displaying list. So first function we have is list line plot, and then we have the list. So 1 3 5 4 and 1 2 1 4. So what it does is basically 1 and 3, 1 3 and 5. It connects all of them with a line, and then like 4 and 1. It goes down again from 4 and 1, and then there's 2 1 4. So it's like 2. No, I think it's 2, then 1, and then just it's again 4.
Yeah, so it's the same as list plot, except now when we draw the dots, we draw lines between them. So you can scroll down to here. If you scroll down on your screen, you see it's the same as this, except we just draw a line between them. So list plot versus list line plot.
Now, so I think list plot and list line plot are just like one is joined and another is not joined.
Yeah.
For one side. That's it. And now we have bar chart. So bar chart just like makes the bar for the specific number. So here we have a bar of length 1, then we have a bar of length 3, and we have a bar of length 5, and etc. And lastly we have a bar of length 4. So if I put my pointer over the bar, it will show the number of the bar length simply. And I hope you good with the bar chart, then I have the pie chart. So what pie chart does is like it represents the data of the list in a circle, in a circle. So it just says pie chart, and to make a pie chart, I just need to type pie chart and then like put the list what I need to display, and I can like put my pointer over any of the portion of the pie chart, and it will show the respective numbers. And now I have number line plot. So number line plot basically does is like it plots the numbers on the number line. It's maybe one of the most simple thing. So like it's just plotting the number on the number line. And sometimes we need to make columns. So to make columns, we can just write column and then put the put the list in the function. So if I try to do something else with it, I'm just trying to annotate it.
Yeah, and column is also something. Oh, actually, you go ahead, and then I'll add this in a minute.
Yes, Rohan, can you?
Oh no, I said you can show this what you're about to say, and then I show, and then I'll say what I had to say in a minute.
So I can just like do this, and it will first make a list of. So the function starts from counting over here. So the first thing it does is list from 1 to 5, and then reverse it, and the second, and what is the second function over here, and then does the last, which makes actually the column of 5, 4, 3, 2, 1. And yes, Rohan,
yeah, and I was just gonna say column is also a sort of operation which again can work on a list of symbols. So we could just put column of list E, F, G, H, I without those symbols being defined, and it would just write out E, F, G, H, I. It would just stack those symbols together. So it's another one of those operations that shows the symbolic sort of nature in the Wolfram language. So maybe you just want to quickly run that example, like A, B, C. I don't know if we have those defined. We have those defined since they're showing up in black versus green, blue, sorry. But it doesn't matter. We can, yeah, something like that. You can just type that in.
So now I have mixed all of them. Like, so for
right. So the first element A is actually a list. The second B is a number, and then the rest are just symbols, and they all get stacked. They all get stacked in a column, even though they're completely different types, as you see.
What does the B goes?
B has been defined to 19.
Oh, and what is the A? What is A?
A is defined to the list because we defined A and B earlier in this program, this notebook.
Okay, so nice. I'll just like,
so yeah, that's a good thing to point out. Whenever the value shows up as black, that means it's already been defined to something. When it shows up as blue, that means it's just a symbol without any value right now.
Yes. So the first one is actually a list. So we can just like put a list on a column, and then that's basically. And we can, I guess we can also use arrays here. So let me try to do this.
In the Wolfram language, we need double quotes for strings.
Oh, sorry. Yes. Yeah. So now we have all the types of data types that basically we need in the column. And now I'm moving over to so in this thing we can like make graphics of two pie charts, and then we can use them as an input data also. And like
right.
Here this piece of code creates just like two pie charts and then put them in a list.
Right. Which is just another way of showing the symbolic nature of the Wolfram language, right? Because we can have a list of basic types like strings and other lists. We can also have a list of these complex, more symbolic types like graphics themselves, which is sort of what we were talking about earlier when you can pick up and paste graphics. So yes. I think now we should actually try and transition quickly to chapters 5 and 6. So we have a little time to go over those.
Okay.
Yes. Okay. So I will switch over here. Oh, actually, sorry. I can just take over from your sharing. I think should be able to.
Oh, thank you.
So can you see my screen now? I think.
Yes.
Okay.
Yes.
So let's quickly go over chapters 5 and 6. So chapter 5 is about some other operations we can do on lists. So for example, if we have a list like this and we just add a single number to it, that will broadcast that across all of the elements in the list. So we can do this with any sort of our basic operations. So now we multiply everything in the list by 10 or divide everything in the list by 10. And again, because Wolfram language is symbolic, when we sort of do operations like this that result in decimals or fractions or not whole numbers, it represents them in that way. And we can go through a process of converting them to a decimal form if we want to, but we'll save that for a little later. We can also do operations between two lists in this fashion. So if the lists have the same shape, the operation will work on every pair of elements. So we match 1 with 1 and multiply, we match 2 with 2 and multiply, we match 3 with 3 and multiply, etc. So we can try something like we've done before now. We can create a range to 20 and we can multiply everything by 10. And we'll see that that's 1 times 10, 2 times 10, 3 times 10, etc. And we can do a list plot of that to visualize the output, which we'll have now not sort of the linear thing we were seeing before, but something that rises more rapidly. Or I guess, no, it would be linear. If we did something like this instead, it would be a more rapid growth. And this is just squaring something and raising to the exponent of 2. So some other operations we can do on lists quickly. Length of a list, we'll just take 3. We can sort a list that's not in order. So if I start with bigger numbers and go down to smaller numbers, and I want to sort it into order, it will do that. There's also reverse sort if I wanted it to have sorting the highest elements first. Of course, we could also just do that manually as well through reverse sorting and then reversing. So sorting, then reversing is the same as reverse sort. Yeah, we can also do first and last operations on our list. So I can take the first element of a list and a last element of a list. So I can index them in that way. You can also specifically get a part of a list using the part function. So if I want to get the third element of the list, in this case, that's 3. And so that's what I'll get back. Or I could get the, let's see, the 5th element of the list, which I just changed to 4. And so that would give me a 4. And there is a notation to do this without using the part function, like a bracket notation like Python. But that's something we'll go over a little later. So some other critical functions to the Wolfram language and functional programming in general. So these first, last functions that I just introduced you are very common in functional languages, especially in Lisps, because that is basically how they're implemented through this first, last, through this first, last functionality, which is something we'll go over again later. But take is another important function in functional languages. It just takes in a list and it gives us how many elements we specify from the beginning of the list. Or if we make it negative, it takes them from the end of the list. And drop is analogous to that. It drops elements from the beginning of the list and gives us what's left, or it drops elements from the end of the list and then gives us what's left. So we drop the last 2 elements in this example, and in the previous example, we dropped the first 2 elements. So we can quickly do a practice problem to see something like this. Use take and drop to get the sequence of 11 through 20 from range 100. Okay, so you just convert that to text. So range 100, let's just look at what that is first. So we want 11 through 20. So we want to drop everything that's not 11. That's before 11. So that's the first 10 elements, the first 10. So we'll drop the first 10. Oh, that's the last 10. Drop the first 10. And now we want 11 through 20. So we want to take the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 first elements. So we can take those like that. And so that's how we would do that problem. Let's see if there's another problem we might want to try. Make a list of the first 5 squares and cubes, numbers raised to the power 3, sorted into that order. Okay. Make a list of the first 5 squares and cubes. So, okay. So, I mean, this will sort of already sort them, but there's 5 squares and cubes. 1 squared, 1 squared, 2 squared, 4 squared, 5 squared. And we will go over a way that you could actually automate something like this with a simple square expression and then just have it repeat across these numbers, although we'll probably have to save that to next time. So there we get a list. And now we can sort it. So you see that the output below changes because some of the initial cubes are smaller than some of the initial squares, but eventually the cubes sort of overtake and go into the end. So the sorted list is actually different from the order that we originally put it in. So we only have a few minutes left, but I think it's worth sort of quickly reviewing everything we learned about the Wolfram language today. So the Wolfram language is probably one of the easiest languages to pick up, if not the easiest, from the languages in the Paradigm Language Conference, but it's also very powerful, especially because it is easy to pick up. It lets you do some super powerful things very early on. For example, there's no other language where we could have started generating complex plots like this within just the first lesson on the language. And the functional, this mashup of functional and symbolic programming, it lets you do certain things that are very unique that you can't really do that easily in other languages. And actually, as a way to sort of stress how symbolic the language is, I can also use symbolic functions as well. So in this case, I just have a symbolic function f, which I'm applying to a list. In another language, if I didn't have f defined specifically, that would throw an error. But in this case, we're just treating it as some symbol without a value yet. And so that's a valid expression. And so the ability to do stuff like this is really powerful. And we're going to be exploring what type of stuff that enables and what type of programs it simplifies in some of our other videos. So this was just meant to be a quick introduction to the Wolfram language. Next time, we're going to be exploring some of these chapters in a little bit more detail. And so we hope you're excited about doing that. And we hope you'll join us for our future videos. Mihir, is there anything else you wanted to say before we end?
Thank you everyone for this video. And just like I have myself, Rohan, and Anthony have gone over all the topics, and I think you should just like try to annotate them by yourself and just download the course and try to just run it by yourself. That would be very good.
Yep. Okay, well, we're going to be posting a video every week, so hopefully you'll join us for next week's video. Thank you.